If you have a doubt, especially let's start with H.C. Verma. Let me know of any questions that you have doubts in from H.C. Verma friction chapter. We will start with the discussion of those. There are some particular questions which I anyway want to discuss, but other than that, if you have any doubts, let's discuss the same. So I'm starting with question number 10 of H.C. Verma. Okay, so the 10th question says that we have this situation. There's a block, certain mass resting on a table with a coefficient of friction equal to mu. Okay. It says the angle between the resultant contact force and the normal force exerted by the body on another, or in this case you can say by the surface on a body, is called the angle of friction. Okay. So it says the angle made by the resultant contact force. So let's understand what this means. And normal reaction force. So this is given a special name. This angle is called the angle of friction. And in this particular question, they are denoting it by the symbol lambda. So we have to show that lambda is less than equal to tan inverse of mu, where mu is the coefficient of static friction. Yeah, after we finish discussing the doubts and questions, I will be starting with the new chapter, which will be work, power, and energy. Okay. But of course, I think most of the time in today's lecture we'll go in discussing these questions. So anyhow, let's see. We have another lecture this week, so definitely we'll start with the new chapter. So let's understand the meaning of this question with this free body diagram. So supposing I have a situation where this body is lying on a surface which has coefficient of friction mu. Now, irrespective of external forces, let's just talk about the two forces of normal reaction and friction, which are mentioned in the question. So normal reaction will be a force that acts perpendicular to the surface of contact, and friction will be a force that acts tangential to the surface of contact. So if we are applying some kind of external force which is giving a tendency to slip or making the body slip or whatever, so if we are applying some external force in this sort of direction, then friction will act in this way. So now let's understand this thing, the resultant contact force. So what do we mean by this term? The resultant contact force, let's say R. This is the vector sum of normal reaction and friction. This is what it means. Okay. There are two types of contact forces, both normal reaction N and friction. They are both different types of contact forces. Okay. Therefore, resultant contact force this is the, you can think of it like the net contact force. It is the vector sum of N and friction, or it is the net contact force. Okay. So whenever we are adding up these two contact forces of friction and normal reaction, you can understand that they will act perpendicular to each other. So when we are doing the vector sum of these two, friction and normal reaction, they have to be perpendicular. Okay. So the resultant has to be given by this over here. Okay. So you can see the magnitude of the resultant will become square root of n square plus f square. And this angle that the resultant makes, that will be such that lambda will be tan inverse of f by n, as you can see in the diagram. The angle of friction, that is the angle made by the normal reaction and the resultant contact force. The angle made between them is called the angle of friction. Okay, so now you can see here that the angle of contact is given by this formula, which we have written down over here. So now within this formula, you can see one more thing, that the frictional force is less than equal to mu n. Okay, so when you substitute this over here, you get that lambda is less than equal to tan inverse mu. So this lambda is maximum, and that's equal to tan inverse mu when friction is maximum, and that maximum friction of mu n is acting. Because on the other hand, lambda is minimum, which is 0, when friction acting is 0. So this is the range of lambda between the minimum of 0 to a maximum of tan inverse mu. Okay, that is the meaning of the question. Hope this is clear to all of you. Okay, next we will discuss question number 18. Yeah, Rishi, it is mentioned in the question as well as in the solution. You can just read over here. I mentioned what is lambda. It is. Are you asking about question number 16? In 16, the value of mu is given, not lambda. Okay. Okay, but Rishi, have you understood question number 10, which I've discussed just now? You understood what is lambda, no? Lambda is this thing. It is the angle made with the resultant force with respect to the normal reaction. That is the angle of friction. Okay. Okay, anyway, so next we will do question number 15 and 16. Kunj has a doubt in 15 and Rishi in 16, so we'll discuss. So let's move on to question 15 first. Okay. So it says that the friction coefficient between the athlete's shoes and the ground is 0.9. So imagine an athlete, the friction coefficient between the shoes and the ground, that is 0.9. So that means when the athlete is running, the maximum possible acceleration that can be generated is by the friction. Okay, so when running, okay, if the net frictional force generated on the shoes is F, then F is equal to ma. Okay, so therefore the maximum possible acceleration is equal to the maximum possible friction divided by m. So that becomes mu g. So no matter how strong you are, and therefore how much force you apply pushing the ground back with your feet, the ground can only apply a maximum force which is equal to the maximum friction, which is mu mg. And the ground cannot apply a frictional force of more than mu mg. So therefore, irrespective of whether you're Superman or an ordinary person, you cannot generate an acceleration of more than mu g. Okay, so this is the maximum possible acceleration. So it says that when Superman wears these shoes, you have to assume that the acceleration is maximum. There is no upper limit on the capacity of running for at high speeds. So the minimum time he will take to complete the distance of 50 meters. So assume the acceleration is equal to this A max continuously. Ordinary humans, this will not be the case, but Superman is able to constantly generate that muscular force to generate that kind of friction from the ground. So he's able to maintain a uniform acceleration of A max equal to mu g continuously. Okay, so therefore that displacement will become half at square in terms of time, or you can see that v square will become 2 times a into, but this will be a max into s. So these kind of relations we can use. So find the minimum time he will take in completing 15 minutes, 15 meters. So for this, the answer will become square root of 2s upon a maximum. So that is square root of 2 into 50 meters divided by mu g. So you just substitute the value of mu g, you will get the answer. Okay. Now suppose he takes exactly this minimum time to complete 50 meters, then what minimum time will it take to stop? So after he completes the race, so this is the first part, the minimum time taken for the displacement of 50 meters starting from rest. Now second part, time taken to stop after completing s equal to 50 meters. So what happens is that while decelerating, okay, the motion is like this. If your velocity is in the forward direction, now the friction will be acting in the backward direction instead of acting in the forward direction, giving you a deceleration. So again, maximum deceleration is mu g. So it becomes a relation like this. Okay. So for the displacement of 50 meters, the velocity developed is square root of 2as. So that you substitute as square root of 2 mu g into 50 meters. Okay. And then you substitute this velocity as the initial velocity over here. So 0 should be equal to square root of 2 mu g into 50 minus a maximum into t, where a maximum is again mu g. Okay. So you can see the time taken will be this. Okay. So the time taken to stop will come out by this formula, square root of 2 into the displacement of 50 divided by mu g. So again you substitute mu as 0.9 as g as 10. So you get the answer in seconds. So Kunj, hope this is clear, beta. Okay, very good. Let's move on to question number 16. Yes. Now, question 16 is something similar in concept. So what's happening here is that you have a car coming along this surface. And there's a downward slope like this. The angle of inclination of the slope is 30 degrees. And the car is moving with a speed of 21.6 kilometers per hour. Okay. And the slope is 12.8 meters long. Okay. The coefficient of friction on the slope is 1 by 2 root 3. So show that no matter how hard the driver applies the brakes, the car will reach the bottom with a speed greater than 36 kilometers per hour. So let's understand this, that while on the way down, if friction, brakes are applied, so friction is acting like this on the car. Even then it will have an acceleration downwards. So maximum friction, mu n, will become mu mg cos theta, because normal reaction is mg cos theta. So you can see that even with maximum friction, okay, E will be positive because mg sin theta will dominate over maximum friction. So that acceleration will become mg sin theta minus mu mg cos theta divided by the mass. Okay, so it will have an acceleration of, now g, I think we are told to take 10, is it in the question? Or even if we are not told, let's take it as 10. Into sine 30, which is half, minus mu, which is given as 1 by 2 root 3 into cos 30, which is root 3 by 2. So the acceleration will become 10 into half minus 1 by 4, or 2.5 meters per second square. So now you take the initial velocity as the speed with which the car is starting at the top. Okay, so u is equal to 21.6 kilometers per hour, convert that to meters per second. Okay. And take the displacement as 12.8 meters and take the acceleration as 2.5 meters per second square. So use the relation v square is equal to u square plus 2as. So this will give you the value of v as this thing, 36 kilometers per hour, or it will give you 20 meters per second. Sorry, 10 meters per second. Okay. Which is kilometers per hour. So you'll see that the velocity is this much even when maximum friction acts. That is when you are doing hard braking. That is when the friction acting is maximum. Okay. So any other situation, the velocity will be even more than this. So that answers the question. So even for hard braking, when maximum friction is acting, your velocity will increase from 21.6 kilometers per hour to 36 kilometers per hour because of the steep slope. S is given in the question, beta. Pay attention now. I told you all this data is given in the question. See, everything in the diagram is given. The value of mu is given, the value of displacement is given, the value of 21.6 kilometers per hour, the initial velocity, this is given, the angle 30 degrees, all this is given. Okay, so just finish writing down this question. Rishi, you have the question in front of you. Now you can see in the question it is given to you that it encounters 12.8 meters long slope. So that's sorry, 12.8 meters, not 6. But anyway, okay, this is clear now. No? Okay, let's move on to question number 18. Okay, now this is an important type of question. We have discussed something similar in the previous lecture also, so try it out. 17th question, Rishi, is the similar type now. Coefficient of friction is given to you as 1. Okay, so maximum acceleration in 17 also you take as mu g. Okay, so that is 10 meters per second square. So from that you will get the minimum time in which it can cover the distance. The displacement, the bridge length is half a kilometer, so take S as 500 meters. And from this, S is equal to half 80 square. When you put A as the maximum possible acceleration, the value of time you get will be T minimum. So you will see that you will get the T minimum from this. Okay. So same concept of question here. Now come to 18th question, we'll discuss. So finish writing this down if you're doing it and move on to 18th question. Okay. Try to understand what's happening in the two different parts we'll discuss. So last time we've done question related to 18th. Okay. 18th and 21st, I think we have done in the class last time. Okay, let's move on to question 23 then. Don't think we did the 3-block problem last time, right? We did 2-block problem. Rupesh, I will come to the module question. Just give me some time. I will finish the HC Verma question, then I will come to the module. Okay, so let's do question 23. So we'll use the same type of method that we did for the 2-block problem last time in class. But now we have to extend that to a situation where there are 3 blocks kept on one on top of the other. Okay. Now this is a smooth surface. And this has a coefficient of friction 0.2, whereas this surface has a coefficient of friction 0.3, and the masses of the blocks are given as 2, 3, and 7. Okay, so let's start with the first part. We are applying a force of 10 newtons horizontally on block E, the topmost one. So we have to find the accelerations. So I'll work out the method for this one, and based on that you try out the second part yourself later. Okay. So first thing you can see that the normal reactions, how are the normal reactions looking? The weight of this block is 2g. So the normal reaction acting on this will also be 2g. Okay. On block B, this one will apply a normal reaction of 2g. Its own weight is 3g. Okay. So this will have a normal reaction of 5g. And then the next block, so it's not really important because the ground is frictionless, but anyhow, on the next block, B is applying a downward normal reaction of 5g. C's own weight is 7g because the mass was 7 kg. So the normal reaction applied by the ground on C, that will become the sum of these two, it will become 12g. So based on this diagram, now we can understand one more thing, that now the moment we apply the force on this block, the block E, like this, there'll be one friction that appears like this, because A has a tendency to slip forward, and this friction gives B a tendency to slip forward with respect to C. So there'll be a second friction that acts like this, where we'll understand that F1's maximum possible value is mu1 into this normal reaction, this one, which is acting between A and B. So mu1 you can see is 0.2, and this normal reaction is 2g. So okay, so 0.4g or 4 newtons. This is the maximum value of this friction. Whereas the friction that is acting between B and C, इसका maximum value कितना होगा? This will be mu2 into the normal reaction between B and C, which is NB. So mu2 is 0.3 into this coefficient of this normal reaction here is 5g. So 1.5 G or 15 newtons. Okay. So this is the maximum magnitude of friction that can act. Okay, so now see what is the objective of friction. The first priority of friction would be to give them common acceleration. So assuming no slipping between A, B and C, that is the acceleration of the block A is equal to the acceleration of the block B is equal to the acceleration of C, which is some common acceleration A, suppose. We can make the combined FPD of A plus B plus C and understand that on that combined free body, we have this equation. Okay. This would be the common acceleration. But that now we have to check whether this assumption is valid or not. Just like we are done for the 2-block problem, but now we have to check for 3 blocks. Okay. So now to check the friction needed, okay, check the free body diagram of C first. Okay. So on C you can understand that F2 needs to be mass of C into this common acceleration. So how much friction is required? 7 into the common acceleration 5 by 6. So 35 by 6. That is a friction of less than 6 newtons. It is something like this. Okay. Whereas maximum friction available, F2's maximum value we've just seen is 15 newtons. So that's fine. So this shows us that there is enough friction F2 to prevent slipping between which two? Between B and C. Now next we need to check between F1. This we checked F2. So for that, make the free body diagram of B. So for B, the free body diagram, just take a look at it above once. Okay. So you can see the net force is F1 minus F2. This is what is giving the acceleration to B. This is what is giving the acceleration to C. Okay. And this is what is giving the acceleration to A. So for B to have that much acceleration, the net force on it, F1 minus F2, needs to be equal to how much? It needs to be equal to mass of B into this common acceleration. Now substitute this value of friction. This friction, F2 over here. So F1 minus 35 by 6 needs to be mass of B, which is 3, into acceleration, which is 5 by 6. So how much F1 needs to be? Okay. Now, because maximum friction F1 available is only 4 newtons. So unlike this one, which was okay, this one now fails. This is not possible because F1's maximum value is only 4 newtons. So therefore, there is not sufficient friction available to prevent slipping between A and B. Okay. So that means basically what will happen now. Therefore, acceleration of A will not be equal to acceleration of B. Okay, there's slipping between A and B. Okay, but acceleration of B is equal to acceleration of C because there's no slipping between B and C. Okay, so we have to now solve this. We have to again solve. We have to find these accelerations. So we'll come to that, but just like you to go through this process once. Okay, so first check out how we have understood that there's no friction between, there's no slipping between B and C. Then we'll come to see how to understand there's no friction between. I mean, there is slipping between A and B. We'll see that next. But first, see how we are checking the condition for slipping between B and C, and how we are coming to the conclusion that there is no slipping between B and C. There is enough friction to prevent slipping between B and C. Okay, so this is showing us that there is enough friction between C. Okay, But now this next calculation will show us that there isn't enough friction between A and B. So there's going to be slipping between the first block and the second block, between A and B. Okay, so now that we have understood this, how do we proceed next? So we make a fresh set of free body diagrams. Okay. So what we understand now is that the block A will have some different acceleration, let's say A1, because F is acting here, and over here this friction that is acting, which will be which type of friction? It will be kinetic friction. So it will be equal to mu1 Na. Okay. So we saw that mu1 Na was 0.2 into 2g or 4 newtons. Okay. So from that we will see that F minus this friction will give us this. So force was 10 newtons, this friction we just saw as 4, and mass was 2 kg. So this A1 will come out to be how much? 6 by 2 or 3 meters per second square. So that will be the acceleration of block E. Okay, that is a 2 kg block. Now B and C have common acceleration. Okay, because there is no slipping between them. Okay, so let's say acceleration of B is equal to acceleration of C is equal to A2, suppose. So again, what we can do now is make a combined free body diagram for B plus C. So on B plus C, there is this friction acting, which is kinetic. Okay, giving this a common acceleration of A2. So now for this, the equation will become, so this is combined free body diagram of B and C. So mu1 Na will become the combined mass, sorry, of B and C into this common acceleration. So this friction we just saw above is 4 newtons and the masses are 3 and 7 kg. So this common acceleration will come out to be 4 by 10 or 0.4 meters per second square. Okay. So that becomes our answer for the first part, that when we are applying a force of 10 newtons on the 2 kg block, okay, the accelerations will become like this. For the 2 kg block, the acceleration will be of 0.4 meters per second. So this becomes the answer for the first part. No, they don't have separate acceleration, but acceleration of 3 and 7 kg block is common. Okay, see, this is a common acceleration. Whereas acceleration of the block A this. Talking about the second part, it's a different matter. I'll come to that. So in the second part, now you're applying the force on block B. So try this yourself now on that system of blocks. Now you are applying the force on this one. Okay. Okay, so I want you people to make the free body diagrams of this and again approach the problem in the same way. Start with the assumption that if there's no slipping, then how much is the common acceleration? Check the condition on friction after you've considered the common acceleration, and by comparing the friction with the maximum available friction values, you can see whether or not there will be slipping. So let's check out the free body diagrams and the limiting friction, etc. So individual free body diagrams will look like this. When you apply force on this one, this friction will act backwards. This friction will also act backwards on this, so forwards on this. Okay. And of course, F1's maximum value was 4 newtons, and F2's maximum value was 15 newtons. That's the same as the above diagram we had made. Okay, now let's understand what happens when the value of the force is this much. So again, if we assume common acceleration, assuming no slipping, that is A, B, and C move together as one common block. Okay. So make the combined free body diagram. So this will give us the same thing. Okay. Now for this common acceleration, we have to check on friction. So this time the individual FBDs we'll use to check friction are these ones. These ones. So to check friction needed. Okay, so first check for F1. So for that, look at A's free body diagram. So F1 should be equal to this much. Okay. So that is 2 into 5 by 6. So that is 5 by 3 or 1.67 newtons. Now that's all right, because you can see F1's maximum value is 4 newtons. So you can see that this is telling me that there is no slipping between A and B. That I've got. Okay. Now I also need to check the friction between B and C. So to check F2, look at C's free body diagram. So F2 is equal to mass of C into this common acceleration. So mass of C was 7 kg. So 35 by 6. So that is again newtons approximately. And that's again all right, because the maximum friction available is 15 newtons. So this is definitely available. So there is no slipping between B and C also. So now this time overall what we'll understand is that there's no slipping anywhere, neither between A and B nor between B and C. So for the second part, when we apply the force on the middle block instead of the top block, instead of A, when we apply the force on B, then what is finally happening is that they will have the common acceleration of 5 by 6 or approximately 0.833 meters per second square, and no slipping between A or B or C. They all move as one common block. So this is a very important type of question and a very important method of solving this type of question. So make sure you note this down, people. Okay. Now this is the C part of this question also, but I'll leave it out for you to work out yourself. So finish this and we will come to question number 28 next. So finish taking this down and go through the question number 28. Try to make the free body diagram yourself. I'll explain the question.
Wait. No.
Okay, very good. Let's move on to question 28. Now this is a little bit of tricky question, so make sure you pay attention and understand. So in this example, we have a rectangular wedge kind of thing with a system of pulleys. So somewhere or the other, the constraint relation will have to be used. Okay, and not only that, there is a block against it which is sliding down on this even as this is going to be moving. Okay, so that means we are going to look at the motion of an object or the free body diagram of the smaller block in the frame of the larger block which is accelerated. So that means this will also include the concept of non-inertial frame and pseudo force. That's what makes this question extra important now. So anyhow, let's discuss. Okay, so this is our system of pulleys. So now the ground is rough, okay, and coefficient of friction between the two blocks is mu1 and between the bigger block in the ground is mu2. So this surface is having coefficient of friction mu1, this is having mu2. Now what we have to understand here is that the bigger block will, because of the tension in the string which comes as a result of gravity pulling down this smaller block. So the tension acting also pulls the heavier block, okay, such that it has a tendency to get pulled in this direction. Okay, so the heavier block is, let's say, having an acceleration a, and this block is having an acceleration, let's say, a prime, but this is with respect to capital M. Okay. Why you have to understand is with respect to capital M is because, see, what is happening if you're in the frame of capital M. In this frame, you will see this block going down like this. You see it going down like this. But if you're in the ground frame, what you will see is something different. You will see that with respect to the ground frame, the motion of the smaller block is somewhat more complicated. It doesn't go straight down. With respect to the ground frame, the smaller block was here initially. After some time, the wedge has moved here, and the smaller block has moved here. So the direction of motion is not like this. The direction of motion is like this. Okay. So this is the motion of small m with respect to ground, whereas this is the motion of small m with respect to the larger block, capital M. So that's why we are taking this downward acceleration as the relative acceleration. This is with respect to capital M. Okay. So it is relative to capital M, like that. Okay, so that's one thing. So now see, the first thing is that A prime will be equal to 2A from thread length conservation. Okay, if this block If this block moves by a distance x, then how much thread length gets released? 2x thread length gets released. Okay, but during that time, if this block has come down by a distance of y, then how much thread length has got pulled by this one plus y? So this should be equal to L. So that's how we have y is equal to 2x. So that means a prime is equal to 2a. So this is our first equation, which is the constraint relation. Okay. Now the next thing we'll do here is we will make the free body diagrams of capital M in ground frame and small m in the non-inertial frame of capital M. Make these free body diagrams and write the equations. So from that we will find A and A prime. So I've given you some hint about how to proceed. Okay, so make these free body diagrams so that you can verify your method when I'll be solving this next. Okay, so let us also, before we get into the free body diagrams, individual FBDs, let's understand the interaction between these two blocks. Okay, so between the wedge and the block, there will be a normal contact force like this. So the wedge will apply on the smaller block a normal reaction forward, and this will apply a normal reaction backwards. And also there will be friction. So the block is sliding down. So the friction on the block will be upwards. It will be kinetic friction, and the friction on the wedge will be downwards. Okay, so we have to keep all these forces in mind when we are looking at the individual free body diagrams. Okay. So now let's start with the free body diagram of the larger block, which I said we will make in the ground frame. So FBD of the larger wedge or block, whatever, capital M. So that is with respect to inertial frame. So first and foremost, on that, remember there's also this pulley attached over here. So we have to keep into account the forces that are acting on the pulley also. Okay. So now let's see all the forces which are acting. So first of all, in that diagram above, you would have seen there are a number of tensions which are acting, because the thread is pulling the pulley towards the right, pulling it down over here. Also, the thread is attached over here. So there are three separate places where tension is acting, two of them horizontally, one of them vertically. Okay. Then there is the interaction between the block and the wedge. So the block is pushing the wedge back like this with some normal reaction. Okay. And the block is also applying a downward frictional force on the wedge, which will be kinetic friction. So this kinetic friction will in fact be mu1 into n. In fact, let's do one thing. Let's call this normal reaction n1. This is the normal reaction between the wedge and the block. Okay. So we have covered all the interactive forces. Now, of course, there is also the weight of the wedge and the normal reaction with the ground, and also friction with the ground. Okay. So three more forces are remaining. So those are going to be, as I told you, the weight of the wedge itself, okay, capital Mg, then the normal reaction that the ground is applying on it. So let's take that as N2. Okay. And because the wedge is slipping towards the right, there'll be a friction that the floor is applying on it towards the left. So this will also be a kinetic friction, but of mu2 N2. Okay. So this is N2, this is Mg. And in this frame now, this has an acceleration of E like this. Okay. So let's put together all these forces, because it's very confusing like this. So horizontally there is 2T, vertically there is T. So tensions are taken care of. Okay. Then there is this normal reaction N1. Okay. There is this normal reaction N2. There is weight Mg. So normal reactions are taken care of, weight is taken care of, tension is taken care of. Now the frictions. So there is this friction that the block is applying on the wedge. This is F1 or mu1 N1. And there is the friction that the ground is applying, which will be like this, which is mu2 N2. And under the action of all these forces, this has an acceleration E. Its mass is capital M. Okay. So along the vertical direction, let's balance the forces. So N2 has to balance capital Mg plus F1 plus mu1 N1. So that becomes my equation 1. It's quite a complicated equation. You don't make the mistake of writing directly N2 as the weight of the block, the wedge, because there are these two other frictions also involved. Okay, so this is tension. Yeah, so there's this tension plus F1 plus Mg, that all is balanced by N2. Whereas along the x-axis, the net force you can see is 2T minus mu2 N2, and that should be equal to capital MA. So this is your second equation. Okay. Now in these equations you can see A is unknown, N1 is unknown, N2 is unknown. So you have three unknowns. So two equations are not enough. So obviously we have to generate more equations. So for that we come to the, and of course tension is also unknown. There are four unknowns. Not only N1, N2 and A, but tension is also unknown. So we need two more equations minimum. So that is where we come to the free body diagram of the block in the wedges non-inertial frame. So now we are in the non-inertial frame of the wedge, traveling with the horizontal acceleration A, and on that block, now that block has a relative acceleration of A prime. This A prime is relative to the wedge. So that's fine. So first and foremost, there will be pseudo force. Okay. Then there is its own weight. Okay. Then there is the normal reaction that this was applying, the friction that this was applying, and of course the tension in the thread. Okay. So you can see these are all the forces which are acting on the smaller block. Okay. More or less all of them are shown here, but for the weight which is acting downwards and the pseudo force which is acting leftwards, because we are in the frame that is moving towards the right. Okay. So for this, along the x-axis, we'll have the equation N1 is equal to ME. So this becomes our third equation. Okay. And along the y-axis downwards, we will have mg minus t minus mu1 n1 is equal to ma prime. And in this, just recall from earlier, we have seen that a prime was equal to 2a. So this is our constraint relation. So this equation becomes mg minus t minus mu1 n1 is m into 2a. So this equation. Okay. So now remember what we have to solve for. We have to solve for A. So between our four equations, we have to finally eliminate A. Okay, so I'll pick up these equations, and through this and these other two equations, we'll be able to solve for E. Now this combination of equations, we have to solve for E. That's what we have to do finally. Okay, so I'll just leave you with the free body diagram for a bit more time. Just make sure you understand it and the direction of all the forces, everything else. Then the rest part is just algebra, so that's easy. We'll come back to that. Okay, so to solve this, now see what we can do is substitute n1 in this equation. Okay. So this equation becomes small mg minus t minus mu1 ma is equal to m into 2a. And now we need to substitute t, the tension. Okay. So for that, we will substitute n2 here. So 2t will become 2n2 plus capital Ma. So that is mu2 into mg plus t plus mu1 n1, where n1 remember was small m, okay, plus capital M. So t into 2 minus mu2 is becoming equal to mu2 mg, okay, plus mu1 mu2 ma plus capital M. So t we can write as mu2 capital Mg plus mu1 mu2 small m plus capital M a, whole thing divided by 2 minus mu2. So this tension can now be substituted in this equation to find out the value of A. So substitute this here. And ultimately solve for A. And we'll get the answer. So still a bit of algebra left, but now you can see A is the only unknown. So just keep A on one side and the other variables G on the other side, and you will get the answer. Okay, so now before we conclude today, I want to discuss a couple of questions from the module exercise. So I will come to that next. Okay, so just go through this once, and then I want to share a couple of questions from the module exercise so we can discuss those. Still some solving is left for you here, but this is what you need to solve the question finally. Just a bit of algebra remaining here. So this question seems a bit tedious because the numerical values are not given, so you have to solve everything in terms of the parameters mu1, mu2, etc. If the question had given numerical values, you could have seen that these equations would have looked easier to solve. But anyhow, you should know how to solve simultaneous equations like this. It's part of your solving practice in physics. Okay. Yeah, so now let's switch over to a couple of these module questions I want to discuss. So I want you to try out this question number 4 and question number 6 right now. We will discuss them in detail. We will let's understand this question number 4. So here see what is happening, that when you push it, this whole system will act like one common block. Okay, so you can make the combined FBD of M1 plus M2 plus M3. So on that, the normal reaction and weight will act like this, where M is the sum of these three. Okay. So the total mass of this combination will be how much? It will be the sum of these three, which is 3, 2, and 1. So that is 6 kgs. Okay. So the normal reaction will be 6G or 60 newtons. Okay. So now when I apply a force like this, the maximum friction that I'll get will be mu n. Okay. And the coefficient of friction is given to us as 0.4. So 0.4 into 60. So that is 24 newtons. Okay. So the block will start to move. Block starts to move when F is greater than equal to maximum friction. So F is how much now? F is, as a function of time, it is 3t. So 3t should be greater than equal to 24. So that means the tension should be greater than, the time should be greater than 8 seconds. So 8 seconds is when it will start to move. So make a note of this. We'll discuss the next question. Okay, understood. Now let's come to this final question, the sixth one. So here what is happening? Okay, the floor below is smooth, remember. Okay. And you're pulling this rope with a tension. So the boy is pulling the rope with a force. So that force creates a tension in the rope of 50 newtons. So because he's pulling with a force of 50 newtons, the tension in the rope becomes 50 newtons. Sorry. This tension becomes 50 newtons. The rope. Okay. So when you look at the box's free body diagram, okay, you'll have an acceleration in this direction like this. This is 100 kg. Okay. So the acceleration of the box will become 50 by 100 or 0.5 meters per second square. Now when you look at the boy, okay, so on the boy there will be tension acting in this direction. Okay. And the platform from below will be applying a friction on him on the backward direction. So he has an acceleration, let's say like this. And the platform on which he's standing, on that now there is equal and opposite friction, which is giving that also an acceleration. This assuming no slipping between the two. Okay, so his mass is 80 kg. Sorry, his mass, yeah, is 80 kg and the platform is 120 kg. And the coefficient of friction is 0.5. So here you can see that T minus friction will be 80 times acceleration of this system. And for the platform, F will be equal to 120 times acceleration of the system. So combine these two, tension becomes this. So this acceleration of this system becomes tension divided by 200 or 50 by 200. So that is 0.25 meters per second square. Okay, and you can also understand the friction acting from the first equation. The friction will become 120 into 0.25. So that is 30 newtons. Whereas the maximum friction available, you can see, is the weight of the 80 kg person, the normal reaction, into ATG. So there is a lot of friction available. 400 newtons of friction is available. So you don't have to worry about this friction. So now you have seen the acceleration of the block B was that much. The A and the platform together have a common acceleration of 0.25, whereas B has an acceleration of 0.5. So from this, we can answer all the necessary questions. Okay. So from this, you can find the relative acceleration. You can find the individual. So velocity of the platform relative to the box after 4 seconds. कैसे करेंगे? We'll find the relative acceleration first. So that will become 0.75 meters per second square, and multiply this with time. So that will give you the velocity. Okay. And friction we've already seen how to calculate. It will be in fact a friction of 30 newtons. Okay, so hope this is clear, people. So with this, we conclude the chapter of friction. In our next lecture, we will start with the next chapter of work by energy. But please also complete questions from your module exercise 1 and 2 at least, and discuss any doubts in them with me in the next lecture. As we are doing work energy, we'll keep aside some time for doubts of friction also for the next couple of lectures, and make sure you clear all the doubts that you have and finish all the problems of friction. So that's it for today, people. Wish you all the best.